This is our Physics 12 lesson on elastic versus inelastic collisions. So our last lesson we were looking at collisions in 2 dimensions, and now we're going to be taking a look at how we can then look at determining whether those collisions can be elastic or inelastic. Okay, I'll give you a heads up now. The examples that we do throughout this little lesson are actually still done in just 1 dimension, but just take the stuff that we've learned from the 2 dimensions and apply it to those types of questions as we go through, okay? And you'll be able to see that in our practice questions, okay? So let's just get started here with our notes. Okay, so we'll start off with a bit of a collision review problem that uses a combination of work on conservation of momentum and as well starts bringing in the idea of conservation of energy as well. Okay, so if we look at this first one, what we have is a bullet which has a velocity of 150 meters per second and a mass of 200 grams, hits and sticks to a 4 kilogram stationary block. And in this particular example, we kind of think about the block being suspended, as you can see in this diagram here. Once the bullet hits the block, it then moves off together and it kind of does this rotation, kind of like a swing. It's very similar to that. It's a pendulum type collision problem here. Okay, and what we're actually being asked is determine the difference in height that's attained by the bullet and the block, right? So you can see here, this, as it swings, will go up, right? So we're trying to figure out, well, what's happening there. So we can start with, I'll switch back again. We'll start with actually trying to use our stuff with collisions, using our conservation of momentum to try and figure out what's happening after the collision itself, right? What's the velocity at which that's moving, right? Because that's obviously going to help us in terms of trying to figure out a distance that it would have traveled, okay? So let's start with that. So using our conservation of momentum in a collision, we have the following, right? We have the mass of our bullet, so we'll call that M1, which was 200 grams. But we'll need that to be in kilograms, so we'll divide it by 1,000, so it's 0.2 kilograms. We have the initial velocity of that bullet, which was 150 meters per second. We had the mass of the block, which was 4 kilograms, and we were told that it was stationary, so we know that that is 0. Right? What we don't know is what speed is that block and bullet moving after the collision, right? So essentially, what's V1 prime and what's V2 prime? Because they stick together, they'd be equal, but this is essentially our unknown, so I'm just calling it X in this case, okay? So using our conservation of momentum, we can set up that equation of M1V1 plus M2V2 is equal to M1V1 prime plus M2V2 prime, and we can start plugging in our values. So this would be 0.2 times the 150 plus 4 times 0 is equal to 0.2 times an unknown x plus 4 times that unknown x as well. Right, so that would give us 0. What we could do here is multiply these values and get 30. Add like terms here and get 4.2 times x, then divide both sides by 4.2, and we get a value of x, which is our final velocity there of the system, of 7.14 meters per second. Okay, so now we have that. So we've got that kind of final velocity after they've collided and stuck together. The question then becomes, well, what are we trying to find? We're asking how high is it moving, right? So in this case, what we're actually thinking about not only just conservation of momentum, but kind of a conservation of energy system as well, right? What's happening is that you're starting with a movement, so you have kinetic energy, that's then being raised so that kinetic energy is turning into potential energy before it falls, okay? So in that kind of closed system, we can then set up the following, right, where our kinetic energy is turning into potential energy, right? So we're basically saying that our K is going to equal EP or EG, depending on who's writing it down, right? And then, because this would be gravitational potential energy as well, so we have a formula for that. That's 1/2 mv squared. We have a formula for that. That's mgh, right? And there's that height that we're actually being asked to solve for. Okay. Now you'll notice that the mass can cancel here on both sides. And in order to solve for h, we just need to divide both sides by g. So you basically just have 1/2 v squared divided by g is equal to h. We had to use our conservation of momentum in order to be able to find this. That was that 7.14. And we are assuming that we're on Earth here, so this is going to be 9.81. Right, and then that's, if we did this unit analysis-wise, this would be meters squared over seconds squared divided by meters over seconds squared. So your second squareds are going to cancel, one of your meters is going to cancel, and you're just left with a height in meters, and you get a value of 2.60 there. Okay, so what we're really doing here is we're kind of tying in that idea of conservation of energy along with our stuff on conservation of momentum, right? And that's what brings us to that discussion on elastic versus inelastic collisions, okay? So just remember that your kinetic energy is energy that an object possesses by virtue of being in motion, right? So as soon as something's moving, it has to have some sort of kinetic energy, and that kinetic energy is calculated using the following, right? EK is equal to 1/2 mv squared, right? So we just did that quick review of that, and just remember your units there. Again, your mass needs to be in kilograms, your velocity needs to be in meters per second, and then you'll solve and your kinetic energy will be in joules. So when we define whether a collision is going to be elastic or inelastic, it really just comes down to what's happening with the kinetic energy in terms of being lost or remaining the same. Okay, so again, these would be definitions you'd include in your kind of vocabulary list, journal kind of thing. So your elastic collisions. So elastic collisions are collisions in which the kinetic energy of the system is conserved, which means that your initial kinetic energy of the system is the same at the beginning as it is at the end. Okay. With an inelastic collision, that's when the system is going to lose energy to the environment. Okay. So what that means is that your final kinetic energy will be less than your initial kinetic energy, or that the kinetic energy lost is bigger than 0, right? So this would be no kinetic energy is lost, or essentially none is lost, and then here, if you get some that's lost, then your collision would be deemed inelastic. All right, so again, in order to figure out what type of collision it is, or the elasticity of that particular collision, you will need to figure out what is the kinetic energy of the system to start, right? So you'll need, if you have two different objects, you'll need the kinetic energy of both and then add them together, okay? Then you'll also need to figure out, well, what's the kinetic energy after the collision? So again, figuring out the kinetic energy of each of the objects after the collision has happened, and again, adding those together. If those values are the same, then you have an elastic collision. If those values are not the same, right, then you have an inelastic collision. Okay, so again, to figure out how much kinetic energy was lost, you just take what you had initially and subtract what you had at the end. If that value is equal to 0, right, then you have an elastic collision. If it's more than 0, it will be inelastic. You're not going to have it be negative because we're dealing with closed systems here, and they are not going to gain any energy. They can lose it to the kind of surrounding environment, but they can't gain anything because they're in a closed system. Okay, so we'll take a look at a problem, and then we'll look at just an independent practice, but we'll do that one together as well. Like I said, these examples are ones that just kind of show you the idea as to what we're dealing with here in terms of the application of this calculating of inelastic versus elastic. To show you kind of how we're doing that, we're just going to stick to one collision, but you will get some practice problems as well that get you to do it in 2 collisions, where you need to kind of do that same stuff we did in our last lesson, using your angles and your component parts and all that fun stuff. Okay, so let's go into this one. So here we've got a 0.0520 kilogram golf ball is moving east with the velocity of 2.10 meters per second when it collides head-on with a 0.155 kilogram billiard ball. If the golf ball rolls directly backwards with a velocity of negative 1.04 meters per second, was the collision elastic? Okay. We can assume from this question here that the billiard ball was stationary. There's no information given to us that it was also moving at a particular direction, so we're just going to have to assume that that billiard ball to start with is stationary. Okay, and when it gets hit, we can assume that it's going to start moving as well. So we need to start by figuring out, well, what is the velocity that billiard ball is going to end up moving. So here we go. All right, so we have a few things, right? So you've got your golf ball is moving east, and it's coming into contact with this billiard ball. Once they collide, what ends up happening is that the golf ball moves directly backwards, and then the billiard ball is going to move, we would assume, in this direction. Okay, so let's actually kind of show that that's what's happening. So you've got two different masses, two different velocities, and then we've got initials and finals. So we've got the mass of the golf ball, we use G there, and that's given to us as 0.0520 kilograms, and we have the mass of the billiard ball, which is given to us as 0.155 kilograms. We have the velocity of the golf ball, which was moving at 2.10 meters per second east, so we can assume that that's just positive. We are assuming that the velocity of the billiard ball initially is 0 meters per second. We're told that it rolls directly backwards, right? So that velocity of the golf ball prime, so afterwards is negative 1.04 meters per second, and this is what is an unknown right now, right? That's the thing we don't know. So we'll start with that, trying to find what is that final velocity. I mean, if this was given to us in the question, we could go straight into solving the problem on whether it's elastic or inelastic, and we can just start figuring out what kinetic energy is on both initial and final. But as you can see, if you're trying to find the kinetic energy of the system before the collision, okay, it's all well and good to get your mass times, well, I guess we can do it before here. That's not a problem, because we can do mass times velocity squared and mass times velocity squared, and we've got the before kinetic energy, but the question becomes, well, we need to figure out what kinetic energy is lost, so we need to figure out what is that value afterwards, and I can do that here, but I can't do that here. So this is where I need to use my conservation of momentum to figure out, well, what's this, and then I can go into the kinetic energy problem, okay? So again, you're setting up law of conservation of momentum here, where you get the following, right? So it would be like mg bg plus nb bb is equal to mg bg prime plus nb bb prime. You could use 1 and 2 here, it really doesn't matter, okay? So again, you can start plugging in values. So you have this here, 0.052. I'm only holding off on the 0 because I don't have enough space on this board, and that's going to be 2.1. And then this is going to be 0.155 times 0 is equal to, get the 0.052 times the negative 1.04 plus the 0.155 times the BB prime, or x. Okay, so again, that's going to multiply and give you 0, so that can cancel. So to solve for that VB prime there, you'd start by subtracting this from both sides and then dividing it by that mass of 0.155. Okay, so you'd essentially be doing the following calculation of 0.052 times 2.10 minus this term of 0.052 times negative 1.04, and then dividing by the 0.155 to give you that velocity of the billiard ball after the collision. Plug in all that, do the math, and that actually gives you a value. I'm just going to plug it in here of 1.0534 meters per second. Okay. So now that we have velocity after the collision of the billiard ball, we can now start looking at our kinetic energy, okay, before and after. So our initial kinetic energy will come from the sum of the kinetic energy of both objects. So if we look at the kinetic energies to start with here, I'm just leaving these values because they're going to be required, right? So our formula for kinetic energy is our 1/2 mv squared. So if we talk about this as like the initial value, EK of the golf ball in this case will of course be the mass of the golf ball, and then Vg, right, that value squared, and then for the billiard ball, again, 1/2 mass of the billiard ball times the velocity of the billiard ball initial squared. So for this one, we get 1/2 times our mass of our 0.052 times our velocity initially, which was 2.1 meters per second, and we square that, right? So square that, multiply it by the 0.052, multiply it by the half, and we get a value there of 0.02812 joules. No, sorry, that was my final. You get a value of 0.11466 joules. Okay. Initially here, because this velocity is going to be 0, you're going to square 0, then multiply it by a mass, and you're still just going to be left with 0, right? So this is just going to be 0 joules. So your total initial kinetic energy is here, right? This is your initial value, right? So now we have to compare that to what's happening in the final. So again, we do these same things with only a slight change in that it's the final velocity, so we use the prime value, right? So this is then that 1/2 times our mass, 0.052 times the negative 1.04 meters per second squared. Okay, that's that value where we get 0.02812 joules, and if we do this here, 1/2 times the 0.155 times this 1.0, hate it, but what am I going to do? 1.0534 squared, right? You're multiplying all that. And when you multiply all that through, you get a value of 0.086 joules. Okay, so these are your like final values here, right? And then if you add these two together, right, you get a value of, so it's like, this is kind of like EKF here. You add these together and you get a value of 0.11412. All right. So our final kinetic energy was 0.11412, and our initial was 0.11466. And let's be honest, if we're only off there by, we're talking tens, hundreds, thousands, like tens of thousands of a place, we really haven't lost any energy, so we would call this an elastic collision, right? Because our final kinetic energy is, for all intents and purposes, the same as what our initial kinetic energy was there, okay? That's not what I needed to do. There we go. Okay, so again, there's that solution showing you exactly what's happening, right? So first determining the velocity of the billiard ball after the collision, and then finding the kinetic energy before and the kinetic energy after, and then kind of taking the sum of both and comparing it, and seeing that what you get is essentially the same, right? Okay, so again, this would be the independent practice problem where you could, again, choose to pause this video, give it a try on your own. I am going to just do it for the sake of having another example here, but it is going to be pretty much the same, okay? In this one, though, I am going to add being able to calculate a percentage in this as well. It's what we haven't discussed, but you can determine the percentage of elasticity that's happening in a problem by taking your final kinetic energy and dividing it by your initial, and that'll give you the percent elasticity that you're dealing with. All right, so in this independent practice, what you've got is 2 train cars of identical mass, 10 kilograms. So they're not like real trains, obviously, just more like toy trains. They are colliding and they move off as shown. So what you're seeing here is that they're both moving towards each other here. They hit and then they don't stick together and keep going. They pull back apart, right, and travel in opposite directions. So the left car was initially traveling at 2 meters per second right, and the right car was initially traveling at a velocity of 3 meters per second left. After the collision, the left car is traveling at a velocity of 2.5 meters per second to the left. What type of collision is occurring? So once again, in order to be able to figure that out, we need to be able to compare kinetic energies before and after the collision. The before the collision is not a problem. It's the after the collision part that's tricky because we do not have the velocity of one of the vehicles. So that's where, again, that law of conservation of momentum comes into play. All right, so if we go through this, try and do this one quickly. All right, so like I said, what we need is that second train's velocity, right? So as of right now, I'm gonna need a new marker. Let's see if the blue one's got anything left. Okay, so M1 and M2, we both know their mass. They both have a mass of 10 kilograms. We have the velocity of the first train initially is 2.0 meters per second, and its velocity after the collision is 2.5 meters per second in the opposite direction, so I'll give that a value as negative. We know that the second train's initial velocity was moving to the left, so negative 3 meters per second, and its velocity afterwards is unknown. Based on the diagram, we know that it's going to the right, but we don't have a value for that. All right, so again, setting up that law of conservation of momentum, I'm not going to write out, I'm going to write out the formula, let's be honest. M1v1 plus M2v2 is equal to M1v1 prime plus M2v2 prime. All right, so once again, we just start filling in these values, and this is what we are looking for, right? We could even rearrange this equation right away, right, and call this M1v1 plus M2v2, you're going to subtract this, so minus M1v1 prime, and then you'll take that whole thing and divide it by M2, and that'll give you your V2 prime, right? So then it's just a matter of plugging in the values. So you've got 10 times 2, right, plus 10 times negative 3 minus 10 times negative 2.5, all divided by 10, okay? And then that gives you the value of the train, and when you do that, right, so 20 minus 30 plus 25 divided by 10, and you get 1.5 meters per second, okay? So now we have that value, and it is positive. So that's helpful. So now we go for kinetic energy initial and kinetic energy final, right? And we can combine that and do it in one step. Say, okay, well, EKI is going to equal our 1/2, not 1/3, 1/2 M1 V1 squared plus our 1/2 M2 V2 squared. Okay, so that's 1/2 times 10 times 2. So I'm using my initial values here. And the 1/2 times 10 times negative 3 squared. Okay, so you do that. That's 20. That's 45. So add them together and you get 65 joules. Okay, so there's our kinetic energy to start with. And then you can do the same thing for final, right? So it's just, all right, now this is EKF, so then this is V1 prime, and then this is V2 prime. So what changes is that this velocity is now negative 2.5 meters per second, and then we're squaring that, and then this is the 1.5, and being squared, right? And you do that, and you get 31.25 here, 11.25 here, add them up, and you get 42.5 joules as your EKF, right? And again, we're comparing that to our EKI, which was 65 joules, right? That is a significant amount lost in terms of kinetic energy, which means that this particular collision was an inelastic collision. All right, so we've got an inelastic collision happening, and if we wanted to, we could find the percent elasticity by taking our EKF and dividing it by our EKI, right? So if we did 42.5 and we divided it by 65 and then multiplied by 100%, we get a value of a 65% elasticity, right? So it's kind of showing us how much kinetic energy is still maintained throughout the problem. Okay? All right, so that's that. And then, like I said, what you've got to work on now are a couple of questions from the textbook, right? These are the correct ones for the textbooks that you have. Again, if you don't have your textbook with you, though, let me know. I'll send you a screenshot of the questions so that you can have them. All right, so there's 2 questions there, and then you also have a collisions worksheet as well to work through, right? And again, there will be questions that are going to be dealing with angles that you'll have to apply what we've been learning in terms of the 2 dimensions to this same type of idea, right? But it would just be kind of doing that extra work, breaking it up into its component parts, right? So it's like, that's why there's only 2 questions, because they might take you a decent amount of time along with that worksheet. Okay, so any questions? Again, first refer to the solutions, see if that kind of solves the problem. If not, you are more than welcome to shoot me an email or request a Google Meet session, and we can try and answer some questions via the whiteboard at my house if we need to. Okay.